Hey guys, let's talk about graphing motion today. So, welcome, and let's kind of get straight to it. Position versus time graphs. We are going to have x-axis always is going to be time, and the y-axis is going to be position. Now this can create some confusion, so if I just were to make a very basic sort of xy table or xy graph here, this being the x-axis, we are going to make it time, and this being the y-axis, we're going to make a position. Now here's the confusing part, is that position can be represented typically with the letter x. So this is not going to be an x, it's x-axis, but that's not a variable x. This is the variable x. You can see how that can be confusing. Just be very careful. Also keep in mind that this could be the letter y if it was vertical motion in the y-axis of dimension of space. So with position, velocity, and acceleration, all three are going to have very similar sort of parameters with them, and they're all going to follow pretty much the same rules. So let's kind of take a look at that. Slope is going to be velocity from this graph. So let's say, for example, I have, let's say, position 1, 2, and 3, and of course I could extend it farther down. This would be a -1, -2, and -3. So let me see if I can label those real quickly. Poorly, but you have to excuse me for a moment. And then of course we have time, so 1 second, 2 second, 3 second, and 4 second, and so on. And what, let's see, would be happening if we had something like this? What if that was the motion that I wanted to express? Well, in that case, at time 0, the object is at position 2. And then after 1 second, it is still at position 2, and still position 2, and still position 2 as time progresses. So this object is not moving, and it has a slope of 0. So it has a velocity of 0. It's not moving. What about something that looks something a little bit more like this? Yeah, it's close enough. So I was trying to see if I could get it to have a slope of 1. I think I actually need to change that slightly. Let me see if I can get that done. Make it a little bit higher, maybe that's better. Okay, so after 2 seconds, it's at position 2. After 3 seconds, yeah, it's pretty close. It's at position 3, and so it goes up 1 over 1, up 1 over 1. It has a slope of 1, which means it has a velocity of 1. The slope is positive, so it's moving in a positive direction. To express it moving in a negative direction, it'd be something like that. This would be a slope of -1, where it is moving in a negative direction, has a negative slope. You, of course, can't move backwards in this sort of direction. You're always progressing to the right because you can't move backwards in time, unless you're driving a DeLorean. But we'll move on to that for next time. And as long as this is a straight line, it is constant velocity. So just to give another example, if I have something that looks something like that, then that is a changing velocity. It is accelerating. Its velocity is changing. Okay, so here's an example. I have something that it goes up 20 centimeters over 0.1 seconds. Up 20 centimeters over 0.1 seconds. And so the velocity is going to be equal to the change in position over the change in time, and in this case it is changing by 20 centimeters in a time of 0.1 seconds. Our units are centimeters per second in this case. 20 divided by 0.1 is going to be equal to 200, and that is again centimeters per second. This is the same thing as 200 meters per second, so either one would be fine. And it is positive because it's a positive slope. Let's look at some other examples. So we have here a couple of different cars. So the first one I'm going to be is this red car here. Let's look at that example. And it is a positive slope, so it's a positive velocity. Again, this is a position, right? So position versus time graph. And let's call these meters. Meters, and that was a T, and these are seconds for units. So as we progress up, it goes up 5 over 1, up 5 over 1. So the slope is 5, positive specifically, so it's a 5 meters per second. The yellow car, that is a changing slope, so it is accelerating. And in fact, we can figure out the slope approximately for the first segment. Looks like it goes up, about 2, and then it goes over 1. So it's about a slope of 2 initially for this first bit here. But then in this next bit, it goes from about the 16 to about the 32 or so. So we're looking at about a 16 slope of 16, and so it's clearly increasing its velocity and increasing in a positive direction. So not only is it moving in a positive direction, it's accelerating in a positive direction. And I'll get to some other examples pretty soon here. Let's look at the green one. So the green one is at the 15, and it continues to stay at the 15. It is a velocity of 0. It is at the 15 meter mark, and it is just staying there. And the orange car has a negative slope, so it's moving in a negative direction. And its slope, let's see, it goes down 30 and over 3. So that would be a slope of negative 30 over 3, which is negative 10. So it's moving at a rate of negative 10 meters per second. And that's negative direction, moving at a constant velocity. Straight line, constant velocity. Let's see if I can look at another example here. Change up some colors. Let me do another sloped line, but let's see what it looks like if it's something more like this. Okay, so what's happening there? We'll look at the slope initially. It's a very high slope. It's probably maybe, I don't know if it would have kept at that trend, it would probably be at like the 40 mark. So it's like a 40 meter per second velocity at first, or I could try and keep that, try and extrapolate and see what it looks like after 1 second. It's about 40-ish. And so that's about 40 meters per second initially. And then later it goes to a slope of 0. So it's moving real fast and it's slowing down. And, let's just assume that maybe just continues along in that path and it will just come to a stop. Alternatively, it is possible that it just kind of slopes right back down. And this would be like almost like a boat that's going real fast, puts it in reverse, slows down, slows down, slows down, and if you keep it in reverse, it's going to eventually just start going in reverse. And so that's what's happening there. Okay, so let's see what else we can look at here. All right, so let's take a look at these segments. In this segment, we have something that's moving at a pace of, let's say, this goes up to the 4 and over 2. So 4 over 2 is 2 meters per second. So this is a 2 meter per second velocity. And then what does it do here? It suddenly stops. It comes to a stop, and it doesn't move for, let's see, 1, 2, 3 seconds. It stopped for 3 seconds. And then it suddenly moves in a negative direction at a pretty fast rate of speed, too. So it's moving at negative, let's see, it goes down 4, 9, and it does that in 2. So about 4.5, negative 4.5 meters per second. And then it suddenly changes direction and is now going in a positive direction. And so this is a fairly slow pace because it's a fairly slight slope. All right, so let's look at position, velocity, and acceleration graphs and take a look at what those will look like for each of them. So let's see here. What's it look like if I just have something that looks like this? That's the 1, 2, and 3 meter mark. And so it is staying at the 3 meter mark the entire time. And so what is the velocity graph going to look like? Well, it's a velocity of 0 the entire time, so it's right on the x-axis. The velocity is not changing, so the acceleration is going to also be 0. Pretty simple and pretty easy examples. Let's make that a little bit harder. Let's give something that actually does have some sort of velocity, and I'm going to see if I can make this consistent. So we have a slope of approximately 1. Let's see if I go, yeah, it looks like about 1 right there. And so, right, it goes up 3 and over 3. That is a slope of 1. Well, what does that look like on the velocity graph? Well, If this is a slope of 1, then I am going to look at this mark right here. This is my 1 meter per second mark right here, and so that's where my line goes. It is a horizontal line. Why is it horizontal? Because the slope of this line does not change at all. It's at 1 meter per second here. It's at 1 meter per second here. And so that means that my line should be on the 1 meter per second mark the entire time. So what does the acceleration look like? Well, what's the slope of the line here? The slope of the line here means that I'm going to go on that value on the acceleration graph. So this is not changing its velocity, so it is accelerating at a rate of 0. It's actually not accelerating. Let's look at the next example. Let me kind of get rid of these. If I can, there we go. And let's see, let's change up colors again. Let's make it so it actually is accelerating this time. So another fairly straightforward example. Now this one's a little bit hard to actually get real values, but you'll get the idea. So initially the slope looks like it's pretty much 0. So that means that it should start at the 0. And then let's look between this segment here. It goes up approximately 1 and over 1. So right about there, it should be at a slope of about 1, give or take, somewhere around here. And then the slope really increases. Now, it's never going to go to infinity, but you'll get the idea here. That it looks like maybe it's going up 2 for every 1. So maybe over here should be at the 2. Now, I didn't do a great job of it. I did not make this a very good graph. But basically, if I did this properly, where this is actually a truly exponential, right, an x squared graph, then this here should be actually linear. Now, I didn't make these lines great, so you'll have to forgive me on that. But this would be linear, and it would have a slope. What is that slope? Well, it goes up 1 and over maybe 2, up 1 over 2, something like that. So it's about a slope of about 1/2. I'm fudging the numbers, bear with me. So whatever the slope of this is, that's going to make my horizontal line here, best as I can make. So that means that I have a velocity of about 1/2 meter per second, and an acceleration of about 1/2 meter per second squared, excuse me on that. And so that's where I should go, is about the 1/2 meter per second squared acceleration. So this, if you have any background in calculus, these are derivatives, graphical derivatives, and they're pretty straightforward. So whatever the slope of something here is, you put it down at the value here. Whatever the slope is here, you put it down at the value here. So that's kind of the way it works. So let's look at one more sort of more complex example, and just so you can get a feel for what these graphs look like. If I can erase it all, here we go. And so I'm going to make something that is sort of a sinusoidal curve. And let me start it here, and I'm going to see if I can make a sinusoidal sort of curve best as I can. Ooh. Best as I can. I'm trying to still get used to my tablet. All right, what I'd like to do now is to look at the high points and the low points. So I'm just going to circle those, right? So I'm going to look at these points here, the high and low points. And so at this first high point, I want you to recognize, what is the slope of the line at that point? Well, it kind of makes temporarily, just at that moment, it makes a horizontal line, doesn't it? So the slope at those points is 0. So I'm going to track down, and I'm going to make a spot right here. And from that point, is the slope going positive or negative? And it's going negative. And I'm going to make a little slash through it going down. From here, the slope is becoming positive. I'm going to make a little slash through it going up. Slash going down because it's going to be going down. So I'm going to transfer those slashes over. Transfer it over, something like that. And now let's look at these points. Okay, so right here, the slope appears to be 0. And so I'm going to put that one at the 0 as well, and it is also going upwards, right? And this also is a low point. It's going upwards from there. I'll transfer that as well. All right. Now, if this is truly exponential change, than what I've got going on. In fact, I'm going to do one more thing. Let's look right about here. What do you notice happening right there? And right about here, and right about there, and right about there. What's happening there? Those are your points where your slope is at its greatest. So if I transfer that down, just going to make some dotted lines down. Doesn't need to be perfect. Where the slope is at its greatest, that's where we're going to have our peak value in between these marks. So this is at the 0, this is at the 0, and then I'm going to have some sort of peak value right in line with this. Now that peak value, notice that here the slope is negative, so I'm going to be below the x-axis. Here the slope is positive, so I'm going to be above the x-axis. So they're going to be straight lines until I get to that peak, and until I get to about that peak, and so on. Did I do a great job making straight lines? Nope, not at all. But I think you'll get the idea. In fact, I can probably fix these bottom ones a little bit. Maybe that's more like where the peak is, but you get the idea. That's probably a little bit better. So that's how we transfer down to the velocity graph. If this is truly an exponential change, then this is going to be straight lines. And then we kind of do the same sort of thing, right? I go to the peak, peaks and troughs here, and I transfer them. This one's going down, this one's going to be going up, this one's going to be going down, this one's going to be going up. But in this case, acceleration has the ability to have a drastic change. So you're going to scroll down slightly. So it's going to look something like this. All right, so let's make sense of that. From here to here, the object is accelerating in a positive direction. So you are essentially trying to accelerate in a forward direction. Using the example of a car is typically not the best. Instead, we want something more like a boat or a hovercraft or something like that, that in order to slow down, you would actually put the object in reverse. So if you can imagine like a hovercraft or a boat where you're moving forward and then you throw it in reverse, that's going to slow you down. And eventually, if you keep it in reverse, not only are you going to slow down, you're going to even start going in reverse. So here's what's happening, is you have it in its forward sort of propulsion, and it's trying to accelerate in a forward direction. And then all of a sudden you throw it in reverse. Now you're still moving forward because your velocity is a positive velocity. So from here to here, you're slowing down, okay? You're slowing down during that time. You have thrown it in reverse and you start slowing down, and it's right about here that you actually start moving in reverse. So you're slowing down, slowing down, slowing down, and now you're actually moving in reverse, and you are increasing your velocity in reverse, and then it is at this point that you've thrown it back into forward because you're moving really fast backwards, and you start slowing down, slowing down, slowing down until you get to this point. At this point, what's your velocity? It's 0. What's your velocity? Right? You have a slope of 0 here. And so it is at this point, you have it in forward, you're moving backwards but slowing down, moving backwards but slowing down, you come to a stop, and you keep it in forwards, right? So the acceleration graph really shows you in what direction you're trying to apply the force. You're still trying to apply that force in a positive direction. You haven't really changed anything. It's just that the object has changed direction at this point. So you keep it in forwards, and it starts moving forwards, it's moving faster and faster forwards, and then you throw it in reverse, and you start slowing down until you come to a stop. This is where you come to a stop right here, okay? So try and run through that in your head, right? Try and go through it a little bit and see what you can get from that. It does take practice to really visualize what's happening with each of these graphs, and without making the video too long, it might help if you kind of run this back through and really try and visualize what's happening there. All right, so I'm going to leave it at that, and hopefully that does help you guys out with a little bit with learning how to interpret motion graphs. Until next time, you guys have a good one.